Okay, so in this video we're going to cover working with derivatives of trig functions. There are 6 different ones that you will need to know. You can derive all of these. However, it's really going to take a lot of extra time and it'll be way more efficient if you just get very familiar with them. I don't want to say memorize, but yeah, you need to know these by heart. But I will point out some things to you to try to make that a little bit easier. So the first 2 I've made a video on where these come from if you're interested, but the derivative of sine is great because it's just cosine x. The derivative of cosine x is almost as great, but it's negative sine x. Then we have the derivative of tangent x being secant squared x, cotangent x giving us negative cosecant squared x, and then the derivative of secant x is secant x tangent x, so it kind of shows up in its own derivative. And similarly, cosecant x is negative cosecant x cotangent x. So 2 things to notice. The derivative of anything with a co in it always results in something negative. So I've put all of these over here on the right, and you'll see that for each one there's a negative as part of the derivative. So that's one thing to keep in mind. The second thing that you might feel like looks somewhat familiar is that they're paired up, right? So tangent has to do with secant, and secant has to do with tangent. Cotangent has to do with cosecant, and vice versa. And these are the same pairs that we find in our Pythagorean theorem, or our Pythagorean identities for trig functions. Okay, and the same is also true, obviously, for sine and cosine. And speaking of the Pythagorean identities, just in general, you need to make sure that you're still very familiar with all the reciprocal identities. You'll need to know those to derive those last 4, as well as the quotient identities. And then here's our Pythagorean identities if you haven't looked at those in a while. You will need to know these in addition to learning these new derivatives. Alright, let's jump into some examples. So for our first problem, we're going to find the derivative of y equals x squared minus 1/2 cosine x. Alright, so we'll be using the power rule here. So dy dx equals 2x to the first, or 2x. This is a constant multiple here, so remember, he just gets to stay out front and we actually derive the function. So that's where we're going to refer to our rules, which we will soon know by heart, but the derivative of cosine is negative sine x. Okay, and you'll find with trig, one of the trickier parts is knowing if you can simplify something or not. However, in a problem like this, it's pretty straightforward and just becomes plus 1/2 sine x, and that's it. Okay, for our second problem, we're going to find the derivative of y equals sine x tangent x. Now what you need to realize here, whenever we write trig functions out, a lot of times we don't bother to put a multiplication sign, but that's indeed what's happening here. So we're going to have to use the product rule when we derive it. Okay, so first is going to be sine x times the derivative of the last, which would be the derivative of tangent x, and that's going to be secant squared x plus last d first. And the derivative of sine, that's one I actually remember pretty easily. That's just cosine. Okay, and now we're going to clean up if we can. Alright, so secant squared is 1 over cosine, so that's not going to simplify at all with sine. However, looking at this second pair being multiplied, tangent is sine over cosine, and if we're multiplying that by cosine, we can definitely clean that up a little bit. So the first part is just going to say sine x secant squared x, and this part over here will actually be able to simplify to just a good old sine x. Okay, So our final answer in its most simplified form will be sine x secant squared x plus sine x. Okay. Now, if you're just doing work for me or on a free response question, you can absolutely just leave it like this if that's all you need to do. However, on a multiple choice question, chances are they're probably going to simplify it as much as they can, and these don't look the same. So you need to be very comfortable with simplifying as needed. Otherwise, you're not going to realize that you did this completely right, because this is what you'll see on the paper. All right, number 3 is to find the derivative of x sine x plus secant x. Okay, so we're going to derive this. We are using the product rule once again here. That's x times sine x. So let's do that part first. So first, d last plus last, d first. Okay, and then we just derive secant squared on its own out here, and the derivative of secant squared is secant x tangent x. Okay, and this one does not look like there's a lot to simplify. We're going to get x cosine x, and then that'll just be sine x plus secant tangent. Okay, that's all there is to that one. Okay, for our next example, we're going to find a second derivative. Okay, given that our original function is x cosine x. Alright, so the first derivative, we're going to use the product rule again. So first, d last, and remember cosine derivative is going to be negative sine x. If it's a cos, it's got a negative derivative. Okay, plus last, d first. Alright, let's clean it up before we go to our second derivative. So this is going to be negative x sine x plus cosine x. Alright, now let's find the second derivative of this. So it's going to be a little bit involved because we're doing the product rule again, and we have that cosine x at the end. So, okay, first, d last plus last, d first, and then again, derivative of cosine we already did, that's negative sine x. Okay, so let's see what we can clean up. We've got a negative x cosine x minus sine x minus sine x. So we have some like terms here we can combine. So we can put negative sine x together in our final answer to a minus 2 sine x. Awesome. And that's it for that one. Alright, for this next example, we're going to bring in some tangent lines and thinking about how the derivative's related to that tangent line. So, where does the function f of x equals secant x over 1 plus tangent x have a horizontal tangent on the interval (0 to 2 pi). Oh yes, we're talking about trig equations here, people. Okay, so first let's just make sure we're kind of understanding what we're looking for. So a horizontal tangent line would be a tangent line with a slope of 0. And if we're talking about the tangent line, the slope of the tangent line, we're talking about the derivative and where it equals 0. So that's basically what this question's asking us to do, and we're going to solve this equation on this given interval. Okay, So let's come down here and kind of set ourselves up. Alright, so again, this is our original function. We're taking the derivative, and we're going to definitely have to use the quotient rule here. So this is my high, this is my low. Alright, let's do this. So low d high, derivative of secant. That's going to be secant x tan x. Okay. Minus high d low. And the derivative of 1 will go to 0. The derivative of tangent is going to be secant squared. All over low, low, or 1 plus tangent x all squared. Alright, we got a lot of fixing to do here. So we're going to have to actually distribute this. Okay, so in this first one, we're actually going to distribute the secant x tan x to 1, which would give us, of course, secant x tan x. But then we also have to multiply it by tangent x as well, which is just going to give us secant x tangent squared x. Okay, and then down here, we're multiplying secant times secant squared, which ends up giving us secant cubed all over this. Doesn't this look so fun? We're about to solve this for when it equals 0. So when does this big old ugly thing equal 0? Well, let's talk about that real quick. Whenever we're solving for when something equals 0 and we're working with a fraction, what makes a fraction 0, right? The only way we're going to get 0 from a fraction is if the numerator is 0 divided by something else. So we actually get to kind of ignore this denominator, because if this were equal to 0, we would just multiply that over and it would disappear anyways, because again, only the numerator is important when trying to figure out when a fraction equals 0. Okay, so we're going to set that numerator equal to 0. Okay, and as with most things from this point forward, when we're solving for something, we're probably going to end up factoring. Yeah. So something that each of these pieces has is at least one secant x. Okay, so I'm going to factor that out front. So let's see here, secant x, and that would leave just a tangent x from the first piece, a tangent squared x from the second piece, and a secant squared x from that last piece. Okay, here's where you're probably not going to like me very much, but remember what I said earlier. You still need to know all these identities. The one we're about to use in this problem is down here, and it has to do with your Pythagorean identity involving secant squared. So as you can see, secant squared, theta is equal to tangent squared theta plus 1, and we're about to plug that in, because right now we have a lot of tangents. So it makes more sense for us to get rid of this extra function that doesn't fit in with the rest of what's in this parentheses. So where secant squared x used to be, I'm going to plug in that Pythagorean identity, and I'm going to make it say 1 plus tangent squared x instead. Okay, and as you can see, this is going to make our life nice, because it allows us to cancel some stuff out by tangent squareds. They're gone. And now we're left with secant x equals, or secant x times tangent x minus 1 equals 0. Okay, and for this we just use the zero product property, which says we set each of these equal to 0 and solve from there. So let's start with the secant x equaling 0. We're thinking of our unit circle here, but we don't normally remember stuff in terms of secant. We're usually only familiar with sine, cosine, and tangent. So we could flip this to 1 over cosine x equals 0. And then if we flip that to just cosine x, then while 0 right now is kind of like over some other number, so if we flipped it, that would be like a 1 over 0, and that's undefined. And cosine's not undefined anywhere on the unit circle. So basically this just means that there's no solution from this little section here. We don't have to worry about that. Let's hope that that's not the case over here. So tangent x minus 1, we would move the 1 to the other side. And then where is tangent 1? Well, tangent is sine over cosine. So basically, where are x and y the exact same on the unit circle? Alright, let's just take a quick peek here. So we're looking for where x and y are the same exact coordinates. So we know it's going to be one of the root 4s in quadrant 1. They're both positive root 2 over 2. Here they're not the same sign. Oh, here they're both negative, and here they're not the same sign. So it looks like pi over 4 and 5 pi over 4 are the two solutions we're looking for. So x equals pi over 4 and 5 pi over 4. Woohoo! That was great. Okay, so for our final example, this one's interesting. Sometimes they'll ask you to find really high powers of trig derivatives. So for this one, I'm going to ask you to find the 27th derivative for the function f of x equals cosine x. Now, why would they do this to you? Well, let's just see what happens when we start taking a couple derivatives here. So the first derivative of cosine x, it's a so it's negative, and it's sine x. The second derivative would be negative, and then the derivative of sine x is just good old cosine x, or negative cosine x. Okay. The third derivative, okay, again we have that negative out front. Then the derivative of cosine is negative sine x. We kind of already did that. But now there's an extra negative out front, so it ends up giving us a positive sine x. So by the time we get to the fourth derivative, the derivative of sine x takes me right back to where we started. So what you'll see with the sine and cosine derivatives is that they cycle through, right? They cycle through, and then it just repeats and repeats and repeats and repeats. Okay, so what am I trying to say? Well, the first derivative, second derivative, third derivative, fourth derivative, this would be the same as the fifth derivative, sixth derivative, seventh derivative, eighth derivative, and I could just keep cycling through here. So it seems like the way we can determine this is just by looking at multiples of 4. Multiples of 4 take us back to the original function. So what we're going to do is look at the remainder whenever our power is divided by 4 to figure out where in the cycle it would end up. Okay, so instead of writing a 5 here, I'll put, well, that would be numbers that when divided by 4 give me a remainder of 1. Instead of a 6 here, that would be like a remainder of 2 when divided by 4. This would be a remainder of 3. And of course, this would be, we wouldn't have a remainder 4 if we're dividing by 4. So that's when it divides evenly and there's not a remainder. So let's take 27 down here and figure out what's going on. So if we divide 4 into 27, that would go 6 times. That gives us 24. So we're getting a remainder of 3, which means that it's going to be exactly the same as our third derivative. So the 27th derivative is going to be the same as the third derivative, and that's just going to give us sine x. Okay, I guess I should say, yeah, sine x. Well, we don't really put, this is what I was wondering about. Here we normally just put doot, doot, doot. There we go. So anytime you get a really high power, it's almost always with sine and cosine and cycles of 4. So that would be the approach to make that problem a lot less scary for you. And that'll conclude our video on derivatives with trig functions.